Okay, so there are two types of particles, really, in the universe. There are fermions and there are bosons. The big difference between them is that you're made of fermions and you're not made of bosons. Fermions make up all matter. They take up space like we do. They're made of quarks and leptons. But you've probably heard of quarks, but you may never have heard of leptons. So, to go over quarks briefly, there's 6 types of quarks. There are 6 types of leptons, but 4 of each of those aren't important. Of the 6 types of quarks, there are top, bottom, charm, strange, up, and down. And of leptons, there are tau neutrino, mu1 neutrino, electrons, and regular electron neutrinos. These ones down here, charm, strange, up, bottom, mu1, and tau, and their respective neutrinos, do not currently exist to our understanding, except for maybe at the heart of neutron stars where pressure is insane. All of these only existed for mere seconds after the Big Bang, and these are the things that we're messing with in the Hadron Collider for a large extent to actually understand what happened at the very beginning of the universe. So all of your current atoms are made up of compilation of up quarks and down quarks. Protons are made up of 2 up quarks and 1 down quark. Neutrons are made up of 2 down quarks and 1 up quark. Obviously your electrons aren't quarks at all. They're leptons. When you hear the word hadron, like in the Large Hadron Collider, hadrons are made up of quarks. And a strong, important note, quarks are controlled by several of the universal forces. Importantly, the most important one is the strong force, which holds quarks together in a proton or a neutron extremely strongly. They are the only thing that is controlled by the strong force, the strong nuclear force. They are also controlled to an extent, though, by the weak nuclear force. If they have charge, they are also affected by electromagnetism, by photons. And of course, they're affected by gravity. So, there's 2 types of hadrons. Ones that, again, generally exist today, and ones that generally don't. Baryons. Those are your protons and your neutrons. There are 3 quarks, 2 up and 1 down, 2 down and 1 up. Those are the most important baryons because these are the ones that exist today. There were other ones at the start of the universe, but we're still trying to figure out what those were. The things we're currently making in the Large Hadron Collider are mesons. Mesons are what happen when you take a quark and an anti-quark and you have them circling each other until they eventually interact and explode. Because if matter touches antimatter, it explodes. And that is a good point to mention. Yeah, these are all the quarks and the leptons, but there's anti-versions of all of these. There's anti-up, anti-down, anti-strange, anti-electrons, also called positrons. Think like PET scans, positron emission tomography. They're real things, antimatter. It's just there's not that much of it currently in the universe. We have to make it. So mesons are when you take a quark and an anti-quark, usually 2, but up to 5, and you have them in one particle at a given time. And you kind of measure how much time it takes before they all interact and annihilate and just become pure energy. And that explosion sends various little energy waves in different directions, and that's how we tell what was inside that meson before it ceases to exist. If you've heard something like there's been new particles discovered inside of the Large Hadron Collider in Switzerland, it is these mesons. There was one recently that had a strange quark in it for existence that had never been found before. We knew strange quarks existed, we just didn't know, we'd never seen them in a 5 quark pair. We'd seen them maybe in like 2 quark pairs, 3 quark pairs, 4 quark pairs. Because 5 quark pairs, in a mixture of quarks and antiquarks, is the biggest mesons we're currently aware of. Mesons being these quark-antiquark pairs. Another weird thing about mesons is that instead of acting like fermions, these things that make up matter and take up space, they actually act more like bosons. They don't take up matter, or they don't make up matter, and they don't really take up space, which is the transition into bosons. Again, fermions make up matter, they take up space. They're made up of quarks and leptons. Bosons do not take up space. They carry the forces of the universe. So, if you're thinking of light, electromagnetism is one of the key forces of the universe. Electromagnetism is carried by photons. Photons don't have mass. They travel at the speed of light, obviously. They interact with charged particles like your protons and your electrons because they affect anything that has charge. But the other bosons also typically travel at light speed. So it's not just light. An example would be gluons. These are the particles that control the strong force that affects quarks. So this one has extra layers of complication to it. There's 8 types of gluons, and they really interact with something called the color force, but to keep things simple, they are what keeps protons and neutrons together. And the force at which they hold them together is just as strong no matter how far apart you try to pull them. It's not a matter of if I take one of the up quarks from a proton and I try to pull it away, no matter how far away it gets, even if it's on the other side of the universe, it'll be being pulled just as strongly back because of these gluons. Hence they call by their glue. They're keeping everything together. Gluons also don't have mass. They also travel at the speed of light. Then you have the weak force. The weak nuclear force, which makes up these leptons over here, the electrons and the neutrinos. So, a Z, a W plus, or a W minus boson are the weak nuclear force. Unlike the other bosons, these have mass, and they affect all fermions, all quarks, and all leptons. But bosons W bosons only exist for a short period of time. Bosons make up electron and antineutrino pairs, or an anti-electron and a regular neutrino pair. You may have heard that if you take protons can become neutrons and neutrons can become protons. And like I said before, a proton is 2 up quarks and a down quark. A neutron is 2 down quarks and an up quark. If an up quark wants to become a down quark, you would per se need to add an anti-electron and a neutrino in the form of one of these W bosons. These things add a charge. They can either again make a proton into a neutron or a neutron into a proton by affecting how up and down quarks decay. Up and down quarks being the only ones that still exist. All these other ones gone right after the Big Bang. So if an up quark becomes a down quark in a proton, it'll become a neutron. And it'll shed a W boson, which is made up of an electron and an anti-electron neutrino. Once that's shed, it'll decay into these respective particles, and that's why W bosons have mass, because electrons have mass, and they only exist for a short period of time. This is getting into the more theoretical part. Gravitons. You may never have heard of a graviton. They're hypothetical, and they haven't been proven to exist yet, but hypothetically they carry the force of gravity. They also don't have mass. They also travel at the speed of light, because gravity travels at the speed of light. We have discovered their wave. Something like 5, 7, 8 years ago, that was like a huge deal, because as we understand it, all bosons have both particles and wave forms of themselves. You might have heard that photons are both a particle and a wave. Well, we discovered the wave of gravitons because of those 2 big black holes colliding, but we have not yet discovered the particle. Yes, also massless, also travels at the speed of light, like all the bosons except for these weak ones, which again, they have mass because they're made up of leptons, and everything over here has mass. Finally, you have the Higgs boson. The Higgs boson is what gives particles mass, fundamentally. If you interact with the Higgs boson particle, which is itself a very heavy particle, so it's the only other boson that has mass, it forces those particles to interact with something called the Higgs field. The Higgs field is a field that exists throughout the entire universe. We're interacting with it right now. And because it imparts a little bit of mass onto you if you're forced to interact with it, it's like molasses. You can't go through the universe at the top speed of light because you're forced to kind of push through all of this extra goo that's all around us. And so only things that don't interact with the Higgs boson can travel at the speed of light. Gravity, photons, gluons that control that strong nuclear force. So yes, anything that has mass is controlled by the Higgs boson. Does that mean the Higgs boson gives all mass? No. Things that have mass do interact with the Higgs boson, but once they do, they're controlled by other forces that impart more mass. So very importantly, gluons, these things that control the strong force. If you think of the equation E equals mc squared, E, energy, equals mass times the speed of light squared. If you want to take that equation and switch it around, mass can also equal energy, as either times or divided by the speed of light squared. So if you have a lot of energy in an area, it actually increases the mass of what is in there. A famous example Einstein used is that hot coffee weighs more than cold coffee because there's more energy in there, and energy does equal mass. So, because gluons are so strong and they hold those baryons, three quark pairs, together so strongly, they impart something like 97% of the mass in the universe, because almost all the energy is there. Photons also impart to you a little bit of mass because they have energy. If they're interacting with a charged particle of yours, like your protons and your electrons, they're giving you a little mass. Again, you're hotter when you weigh more when you're hot compared to when you're cold. So yeah, photons give you a little bit of mass. Higgs bosons give you mass. Importantly, gluons give you mass, most of your mass. Gravitons don't give you mass, they just are what makes you affected by gravity. And gravitons seem to affect nearly everything, because as we know, even photons are affected by gravity. They get sucked into black holes just like everything else. So yeah, I think that's about everything.
Very good. Thanks for doing that, Austin.
No problem.
Good job.
Could have explained leptons better a little bit, I think.
Well, there's more time. You can continue to do it if you want at some point.
True. I'm going to have to think about how I could better explain leptons, other than, again, most of these things like tau and muon and tau neutrinos and muon neutrinos don't exist anymore. They only existed at the start of the universe, but that's the things they're doing in the Hadron Collider. Is even though the Hadron Collider primarily works on hadrons, which are made up of quarks, obviously, if you're turning an up quark to a down quark or a down quark to up quark, like we said earlier, it has to shed a W boson, which is made up of these leptons. So that's the way that they can have these higher charged particles briefly come back into existence. So when you think you're a tau or a muon, it might not be, it's really difficult to understand what that even means. But just think of it as like a far higher charged electron that can only exist for such a short time because its charge is so great, or not its charge, but its energy is so great, that it could only exist when the beginning of the universe was unbelievably hot, and when everything was so incredibly condensed. So we have to recreate those conditions artificially. And like I said, in maybe the center of neutron stars, there could possibly be things like charm quarks or strange quarks still, because there the conditions are so unbelievably insane, they're not really conceivable by mankind. Something like a teaspoon of neutron star dust weighs 100 trillion tons or something like that. So at the center of something that dense, you might have conditions that are more similar to the beginning of the universe. But the more important things to understand are things in this box and bosons. Because once you understand these things, it's easier to understand everything else.
Well, that really helps out. Thanks for doing that, son.
No problem, Dad.
All right, love you.
Love you too.